example should be interesting and educational in many ways. The problem itself is an interesting problem, and then when we implement it, there is a whole bunch of good little issues and techniques to discuss. So I like to use this one as an example of many things. So let's look at the problem, dithering and the Floyd-Steinberg algorithm from the 70s. So what is the problem first? So this is now image processing. So we have a two-dimensional pixel raster image with every pixel getting its color from some palette. So normally we have a full RGB 1 byte, so about 16 million colors. And now the task is that you're given this kind of image with the colors from some wider palette, and then your task is to create another image with the same size and resolution, but using a smaller palette of legal colors that you are allowed to use. And then using a very limited palette with doing this wrongly. So now we can see what the problem is. So how can we, so that we cannot solve this problem just with the trivial algorithm. Loop through all the pixels of the image, look at the color of each pixel, and then find in your allowed palette whatever's the closest color, and then replace the pixel with that color. So the trivial algorithm, so especially if it were done in the restricted binary palette, that the only colors you're allowed to use is black and white, like for example scrolling down here. So here is some grayscale image of the statue of David. So each one of these pixels is black or white, but then we simulate other grayscales, and then especially this color gradients that for the human eye give important information about the three-dimensional world. So all these objects exist in the 3D world, and every image that we have is two-dimensional. It is just that when we see an image like this one here, it's much easier for us human viewers to play along. How do we normally perceive the three-dimensionality? So first of all, the parallax of the eyes, that we have two eyes, so we see everything from two slightly different angles, and then this creates the 3D space in our minds. So looking at the image on the computer screen, so the parallax tells us that this whole thing is a flat thing that I'm looking at. But another mechanism that we use to perceive the depth and the distance is the color gradients, so the way that the color changes across the surface. So we're assuming that the light source isn't artificial to intentionally create this kind of like illusion. So our eyes evolved to be like this eyes and the visual system, because the color gradients provide useful information. So the color gradient, that the color smoothly changes, so that's essential for us to play along, that this is an image to a 3D world. The problem with this trivial algorithm that actually doesn't work is that if every pixel is colored with whatever's the nearest allowed color in the target palette, so then we get blotches of a flat uniform color, and then like this entire 3D so vanishes. So now this is what it looks like, exactly what it is. It's a 2D flat thing consisting of 2D flat things. So now looking at this one, so we can realize that both of these use exactly the same palette, the same very small handful of colors, and yet this one looks so much better than that one. So how is it, what is the magic that from the same ingredients makes a lot better picture? So this Floyd-Steinberg algorithm is a modification to this bad trivial algorithm that I started with. So to do the dithering, the pixels of the original image, they are still processed one at a time. So going the rows from top going down, and then each row left to right. But well, we could modify that to every other row is right to left for a teeny tiny better result. But the simple implementation, so we are processing one pixel in isolation. But now the fundamental difference between the Floyd-Steinberg and this no dithering is that when we take the original pixel and then calculate the one of the whatever, it's still the closest color in the allowed target palette, because every pixel has to be something. So then every pixel is still converted to the closest color, but the difference is that when you take a pixel and make it different than it was originally supposed to be, is that you take this difference, this error, and you spread it across the 4 pixels. So here, so if this one now, this asterisk stands for the pixel that we just processed, and the pixel ends up having a different color than what it was originally supposed to have. So then we calculate this difference, this quantization error, and 7/16 of the error, so we add to the color of the right pixel. Remember, we are processing every row left to right. So when we are processing this pixel, so this pixel hasn't already been processed. The one before, this one has already been processed, so we're not pushing anything there. This pixel already has its final value. But this one to the right, and then because we are processing rows going downwards, so we know for a fact that these 3 pixels also, so right, down left and down right, so these haven't been processed yet. So we take the error and add this much of the error to the intended color of this neighbor. 1/16 goes here, 5/16 goes here, 3/16. If you add them up, these add up to 1. And then now, obvious question, where did this magic weights? Why isn't it 1/4 of error to each one? But there is a method to the madness. I'll explain it in the end. But basically, so whenever, so if we imagine the intuition, let's assume that the picture is grayscale. So every pixel is just one intensity number between 0 and 1. And then the target legal palette that we allow is the pure white and pure black. So pure white is 1, and pure white, well, the widest possible and blackest possible is better phrasing. So then the pure, so the best white is 1, and the darkest black is 0. So then suppose a pixel has a value 0.7. So because we have no choice, we gotta turn it into 0 or 1. So 0.7 we choose to round up to 1. But now the pixel has become 0.3 more brighter than it was supposed to be. Although then this calculation doesn't involve the gamma correction. The problem with this one, so this I'm sure that the people in Photoshop and similar are doing these calculations exactly and correctly all the way down. That this assumes that for example, that the 2 pixels whose brightness is 0.5 together, when viewed from the distance, look the same as 2 pixels, one of which is 0 and one of which is 1, which is not the case because these intensities are not actually linear. So this calculation should be done with the gamma corrected intensity values. But again, so surely the people who write the graphics processing libraries do these calculations. But so the idea, pixel was 0.7 and we made it 1, so means that the pixel has become brighter and therefore the entire image has become brighter. So then to compensate, so the error 0.3 is spread over these 4 neighbors, that they become correspondingly lower. And it might be that this added error, so 7/16 out of 0.3, is enough to change the target color of that pixel. And if it's not, well then the error gets furthermore quantized, and then this approach, when done consistently, almost as if by magic, we can see that it as a side effect produces this kind of a stipple pattern that tries to imitate the original color, here the brightness gradient, to the best that it can. So then viewed from the distance with your eye squinting, so then that looks much better than it has any right to be. So then this produces, if not truly the optimal, at least within this mechanism, the best possible approximation. So this algorithm works for an arbitrary color palette. So let's read through my implementation. there's a couple of things to point out. So now the colors are given as RGB, but now because we are passing these fractional errors, we gotta make sure that they get added correctly. So then in the final result, we quantize, discretize, round everything to the nearest color. But let's keep these intermediate results accurate. The same principle that I talked about in geometric and animation path calculations. Now we would get the aliasing effect in color. It would look just as ugly as aliasing looks in the time and space dimensions. So here, every color is a RGB consisting of three 32-bit numbers between 0 and 1. So we get a whole lot more decimal places than we need. So here is an estimation. Well, should consult the color FAQ or similar document. So then the distance between the colors. So two RGB colors given as two floating point. These always have three elements because we're dealing with colors. So the red distance absolute value, green distance absolute value, and then so because the human eye is not equally sensitive to all the wavelengths, and then go past the visible range. So then we have zero sensitivity to things like radio waves or similar. That we are more sensitive to the green than we are to the red, and then especially to blue. So then how bright something is being as perceived, so then blueness is not perceived as bright as a yellow or green or red, even though they probably do have the same intensity as far as the actual photons are flying. Okay, and then so now here's a principle that we haven't seen before. So here is a method given the color that the pixel was supposed to be, and then given the palette, so array of colors that we are allowed to use. So choose the color that is nearest to the color. And then notice, instead of returning the color as an array, although I now realize that I could just return the individual row from the palette array. But now in all these other methods, so especially when we are modifying, so we're not allowed to modify the palette. So I could return the row here, but the caller gives as an extra parameter an array object. The canonical name, I believe, for this kind of object is out. So instead of creating an array and returning that one, that the caller gives the method an array to fill the answer in. So this way we don't, contrasting to the method that always creates and returns a new array, this one then can recycle the same array object and lighten the load of the garbage collector. So we just loop through the colors in the palette, and if the distance is lower than the best distance seen so far, so then we'll make that color to be the out color. So assign directly to the fields of the out array, and then we are not returning anything in the end. The RGB colors, once they're packed into the bytes of a 4-byte integer, so B is the lowest byte, G is the second lowest, R is the third one, then the highest byte is used to store the transparency, the opacity value, that when a color is used that is partially transparent, the result ends up being the average, the weighted by transparency, the average of the original background color and water. So this way you can render translucent shapes in Java. So there's the bitwise arithmetic. We'll discuss this when we talk about integers and floating points in Java, the bit shifts and the bitwise ands to extract the information. Conversion other way around. So we do the calculation in the higher precision floats, and then we turn them back into ordinary packed integers. Okay, and then so here is now once you decide that the pixel is colored with the actual color, and the pixel was supposed to be this color, so we just calculate the difference into the error array. And then, so this one, when we take the array and divide it, so 3, 16 to 1 and 7 and so on. So then, so given the target array and then the error and what fraction of the error, so modify the components of the target, that if the error is positive, so then the pixel was made brighter than it was supposed to be, so then this pixel becomes correspondingly less bright. So then the multiplier to the error is different for the 4 neighboring pixels. So once we have these as a tool, so the actual dithering algorithm, we can create the result image immediately because we know exactly that it's the same dimensions as the original. Remember, every buffered image being filled with 0 bytes starts as life as being every pixel black. And then the 2 float arrays that we are using. And from the color to the array of colors, so these are now still AWT color objects, and then we just the color objects, so you can ask for the float color components, and then we assign them to the corresponding array. Yeah, the palette scene here. So palette C is the same as this palette, but this consists of color objects, and this one consists of float arrays, the same information in different form. And now here's a handy principle when you're looping through a 2-dimensional structure, that you do need some data for every position, that now the calculation needs only 2 consecutive lines, the line that we are currently processing and the line that is the next one in turn, because the errors from processing the current line, some of them gonna be flowing to the next line. So these arrays of pixels, so this one array of pixels, as long as there is pixels horizontally, and each pixel is a float array of RGB numbers. So that's why the second dimension is 3 in both of these, and as many as there is a width and then extra one that we don't need to worry about the edge conditions in the end. So before looping through the pixels, so then initialize the contents of the first line of the pixel, first line of pixels in the image, and the second line. So from the line number 0 and 1. So the first 2 rows of pixels in the image. And then these are processed 1 row at a time. That we're always processing the car line array, spilling some error to the next line. And then once we process the current line and we don't need it, then the next line becomes the current line in the next round, and then the new next line we read from the original image. So loop to the rows, and for each row loop through the columns. So now Y and X, so we use in the unusual order. So the pixel in the current position of the current line, let's ask what is the closest color that we are allowed to use. It has to be one of these, we have no choice in that matter. And buffered image, so we can set the value of pixel to be that. We just convert back to a packed int representation. And compute that if the pixel was supposed to be this color and we made it that color, what is the difference between the 2 colors, and of the error, so 7/16 to the neighbor to the right. If there is if we're not in the first, we are careful at the left edge, so right and left, down and left. So this exists only if we are not in the first pixel. So propagate the error down and left, 3/16, 5/16 directly down, and 1/16 directly right. Now that we made these arrays one longer than they need be. That's another handy trick to remember. We didn't need to worry when we were at the last position, because there is one more position that we can access even though we are not looping that far. System array copy, that's the best way to copy an array or a sub-array into another one. So this one is hardware accelerated at the low level. And then if we are not in the last line, then from the original image, so now that the next line becomes the current line, so the new next line is read from the original image. So do this for every row and every pixel in every row, propagating the error to the 4 unprocessed pixels. We get the good end result. So now to demonstrate this, if I run it using the picture of Benoit Mandelbrot that I found, so it's in full color, but here is some restricted palettes for Andy Warhol effect, and this one is just black and white, and this one was a 4 or 8. But so we're trying this out, so like a surprisingly small number of grayscale, like a 16 or 32, produces a surprisingly good result here. But as you can see, the algorithm works for an arbitrary palette. And one more thing to discuss, like I promised, like what is the why isn't 1/4 to each one, and why isn't it 1/16 here, and who made up these numbers? So this from a clever argument, if we imagine, suppose you have a grayscale image that is flat middle, that every pixel is 0.5. And your target palette is 0 and 1, so black and white. So what is the only correct way to turn a flat 0.5 image into black and white? So we can argue that the only correct answer is a checkerboard. Now it could be either of either parity, but it has to be a checkerboard. So that's the only reasonable answer for Floyd-Steinberg to the flat uniform 0.5. And as it turns out, this is the weights that does it. So if there is correct weights, so then they have to be these. Any other weights would produce something other than a checkerboard when applied to a uniform flat 0.5 image.